Welcome to the Differential Calculus section. I suggest out of all the different Paper 1 topic videos, you cover this one last, as it uses a lot of the concepts covered in the various Paper 1 topics, and assumes you're already familiar with them. It's also one of the toughest and longest topics in the paper, so if you watch all the other videos in the correct order, it'll also be a natural progression of difficulty level. All this being said, at the very least, you need to have watched the polynomials, logarithms, sequences and series, and functions videos, otherwise you'll be pretty lost. Now that that's out of the way, here's the topics to be covered. First, we'll look at limits, which forms the entire basis of calculus. Then we'll look at differentiation from first principles. Next, we'll cover differentiation rules, followed by equations of tangents, second derivatives, graph sketching, and finally applications, where we'll cover some of the real-life scenarios in which calculus can and is applied. Let's begin. The very first thing to know related to calculus is the idea of limits, which forms the entire basis upon which calculus is built. A limit is the value that a function approaches as a function's inputs get closer and closer to a certain number. To give an idea of what this means, we can use an idea covered earlier of infinite series. The idea was, if you have a series, which as a reminder represents the addition of a certain number of terms of a sequence together. So if you have a geometric series with a constant ratio value falling between 1 and -1, each successive term will become smaller and smaller than the previous one. So adding together an infinite number of terms actually gives a finite value. As an example, say you have a sequence for which the first term is 1 and the constant ratio is half. The first 6 terms would be, so you start with 1, the second term is half, next is a quarter, fourth term is 1/8, next is 1/16, sixth term is 1/32, and it goes on and on. So let's look at various possible series. A series with one term would just be equal to 1. A series with 2 terms would be 1,5, because you'd add the 1 and the half. Series with 3 terms would be 1,75, because you'd add this quarter to this 1.5. A series of 4 terms would be 1,875. So far we can see that the number is slowly increasing, but we still can't tell what value the infinite series would probably have. Let's go a little further with a series of 6 terms, which gives a value of 1,96875. Okay, it increased again, but we can see it's now pretty close to 2, so the infinite series may be equal to 2, but it's just a guess. Let's go a little further with a series of 12 terms. Ooh, okay, it's a little bigger now and has a lot of numbers and is now really close to 2. So it seems very likely that as you add more and more terms, it will slowly get closer and closer to a value of 2. In other words, it slowly approaches a value of 2. And if you actually do the infinite series calculation, you do get a value of 2. So the whole point of this exercise was just to show you the idea of a value slowly but surely approaching a certain number, and this number is called a limit. Now let's see this in action with an actual function, which is where the idea of a limit is actually applied. The function is x squared plus 2x minus 8 over x plus 4. Just by looking at it, you can see that you probably don't want to input an x value that would cause the denominator to have a value of 0, as that would make this undefined. The x value that would make this happen is -4, for which the function is undefined. So this looks like a pretty complicated function, given that it contains x terms in both the numerator and the denominator. But it can be nicely simplified by factorizing the numerator. The numerator can be factorized into x plus 4 times x minus 2. This allows you to cancel the x plus 4 terms in the numerator and denominator, giving the function as just x minus 2. But you can only do this by specifying that x cannot be equal to -4, because that will lead to you having a 0 in the original denominator, for which the function would be undefined. But now, just for interest's sake, what would you get if you substitute negative 4 into the simplified function of x minus 2? You'd get negative 6, but remember that the domain doesn't include x equals to negative 4. If you were to plot this function, it would look like the following. It would be a nice straight line, essentially just y equals to x minus 2, but with the indication that an x value of negative 4 isn't part of the graph, which is indicated with the small white circle over here. You can just think of it as a hole, and since the function doesn't have an x value of negative 4 in its domain, there's a hole present at that x value. But besides that, the graph is just a nice straight line of y equals to x minus 2. So you know that x isn't defined for x equals to negative 4, but we can investigate what happens as x gets closer and closer to negative 4. Or in other words, what happens as the x value approaches 4. Here's an attempt at this investigation. As you can see in the table, I first try to see what happens as you approach it from the negative side, meaning for values less than negative 4. And it could be seen that as you get closer and closer to negative 4, the function gets closer and closer to a value of negative 6, but then it's undefined at x equals to negative 4. Then I also try to approach it from the positive direction with values greater than 4, and this also showed that as you get closer and closer to an x value of negative 4, the function gets closer and closer to negative 6, meaning the function approaches a value of negative 6 from both directions. So we can clearly see that it's supposed to be negative 6 when x equals to negative 4, but unfortunately we also know that it's undefined at that point. This value it approaches is described using the word limit. The way to describe what's happening is saying the limit of x plus 4 times x minus 2 over x plus 4 as x tends to negative 4 is negative 6. And the mathematical way of writing it is, which is read exactly how I just mentioned as described here. The key takeaway from this and what it means is that a function can have a limit at a point where it's undefined. For a general function f of x, the same notation looks like, which is read as the limit of f of x as x tends to a is equal to a value of L. Now, it's very, very important that the same value is approached from both the positive and negative directions for it to be considered as a limit. Otherwise, the limit just doesn't exist. Here's another example. In this example, you've got an interesting sort of function where for a certain collection of x values, the function is represented using one equation, and for another bunch of values, it's represented by another equation. Here, the function is x plus 1 for x values less than 3, and x minus 5 for x values greater than or equal to 3. Now, can you even have a function like this? Definitely. This is known as a piecewise function, and it's something you'll only learn about at university level maths, so don't worry about it. Just absorb the idea I'm trying to explain using it. Anyway, this is what its graph would look like. Notice that the white circle is there again, which means that this graph isn't defined for this x value at x equals to 3. Then this dark circle just means that the graph is defined at this x value using this other line. Anyway, by looking at it, we can tell that from the negative direction, meaning from the left side, the function approaches a value of 4, which is written as follows. The fact that this occurs from the negative direction is indicated with this negative subscript at the top of the 3. And if we look at it from the positive direction, we can see that the graph now approaches a value of negative 2 as x approaches a value of 3 from the right side. What this shows is that the function approaches a different value when x tends to 3 from the different directions. Therefore, the limit as x tends to 3 doesn't exist. So far, we've only looked at some pretty funky sort of functions, but the idea of limits doesn't only apply to difficult functions. For example, we could look at this normal y equals to x plus 1 function, without its domain defined in a funny way. That's how its graph would look. Nothing too surprising. The graph just continues in the straight line. But unlike the previous function, this function would approach the same value of 4 from both directions. Therefore, the limit of y equals to x plus 1 as x tends to a value of 3 is equal to 4. Let's move on to the next part under limits, which is related to finding the gradient of a curve at a specific point. Say you have two different points m and n along a curve. For m, the x-coordinate is a, and the y-coordinate is whatever value the curve function would have for an x value of a. And for n, the x-coordinate is a plus a certain number h, meaning an x value bigger than a. The y-coordinate is whatever value the curve function has for x equals to a plus h. A graphical depiction will give a better idea of the situation. The green line is just some curve described by a function f of x. And the point m is here with x-coordinate a, and the point n is here slightly further down in the horizontal direction with an x value of a plus h. Then say you want to determine the average gradient between these 2 points, meaning the gradient of the following line. You would calculate the gradient by saying y value of n minus y value of m divided by x value of n minus x value of m, which is the a's in the denominator would cancel out, leaving just h, the horizontal or x distance between the 2 points. This is an equation you should have seen before in previous years, and something else you should have heard before is that the gradient at a single point on a curve is equal to the gradient of the tangent to the curve at that point. It would be kind of difficult to determine the gradient at a single point, since so far you've only calculated the value of a gradient using the coordinates for 2 different points. So how would we determine the gradient? The approach is, first consider a line intersecting the curve at 2 points. This would look very similar to the graph we just saw. Then, say you slightly reduce the value of h. Now the line would intersect the curve at a point slightly closer to m. Then if you slightly reduce the value of h again, the line would again intersect the graph at a point slightly closer to m. And if you continue a little further until the value of h becomes 0, the line would now be the tangent to the curve at the point m. You could calculate the gradient using the equation we derived a little earlier, which was f of a plus h minus f of a over h is the average gradient. But since h would be equal to 0, this should be undefined. But we can apply the idea of limits to the gradient equation, which allows you to have a value at a point for which a function isn't defined. If you take the function as this average gradient formula, you can determine the gradient at the point using the following equation. Let's apply this to an example. For the equation y equals to 2x plus 8, what's the gradient at the point 1 and 10? This is the equation of just a basic straight line and not a curve, but the equation works for any function. I'm using this example of a line since we already know what the gradient is supposed to be, which is just 2 by comparing to y equals to mx plus c. Since we already know what the answer is, if we get the same answer using the equation, then we know it's reliable. The equation has an a term in it, which just represents the x-coordinate of whichever point you're interested in finding the gradient at, which would be 1 in this case. Here's the equation again. Then just sub in the a value, giving limit of f of 1 plus h minus f of 1 over h as h tends to 0. F of x is 2x plus 8. So f1 plus h would give 2h plus 10. Then f of 1 is just the y-coordinate of the point, so 10. Then you sub these values back into the equation. Then the two 10s minus each other out, and this whole thing reduces to 2h over h. Since there's the h in the denominator and the numerator, just cancel it out, giving the answer as 2, which we know from before is what you're supposed to get. So the equation works. Notice that eventually, after you simplify everything, the h in the denominator ends up getting cancelled out, and this is quite important. Also, since it's a straight line, the gradient is constant throughout, regardless of which x-coordinate along the line you use. So the final gradient value wasn't dependent on a. Here's another example. For the equation y equals to 3x squared, what's the gradient when x equals to 4? This time the value of a is 4 and fx equals to 3x squared. Then just sub a into the gradient at a point equation. F 4 plus h is just 3 times 4 plus h squared, which simplifies to 48 plus 24h plus 3h squared. Then f of 4 is just the y-coordinate of the point, but this time it isn't given, so just calculate it using the fx equation, and when you do that, you get it as 48. Sub it all back into the equation, and these two 48s will cancel each other out, leaving just 24h plus 3h squared as the numerator. Then you can factor out h, which cancels off with the denominator, leaving you with limit of 24 plus 3h as h tends to 0. You can now sub in the h value of 0, and you'll finally get the gradient as 24. Notice again that the h in the denominator cancels off. This is very important, and you can only sub in the h value of 0 after this happens, otherwise you'll end up with an undefined value. In the previous straight line example, we didn't have this step of subbing in the h value as 0 because all the h's had cancelled out. So there's no h left to sub in a value for. Let's look at another example. For the equation y equals to x cubed minus 0,5 x squared minus 4x plus 3, what's the gradient when x equals to 1,5? So a would equal to 1,5 and fx equals to this equation. Then sub a into the gradient equation. f1,5 plus h would be, and when you expand all the bracket terms and simplify everything, you end up with h cubed plus 4h squared plus 1,25h minus 0,75. And f1,5 is minus 0,75. So sub these all into the gradient equation, then the minus 0,75s will cancel off, leaving just these various h terms. Then you factor out h in the numerator, which cancels off with the denominator h, leaving h squared plus 4h plus 1,25. And since you've cancelled off the h from the denominator, you can now sub in h equals to 0, finally giving the gradient as 1,25. From all these examples, we know that we can get the gradient of a function fx at an x value of a using limit of f a plus h minus f of a all over h as h tends to naught. But if instead we substitute a with an x, this will allow us to get an equation in terms of x that allows us to determine the gradient at any point on the graph. Such an equation is known as the derivative. And with that idea, we move on from limits to the next section under differential calculus, which is differentiation from first principles.